and we'll get started on, this is where we left off last time, and you probably got past this last spring. You, I know, didn't get this in the summer. All right. Anything else before we get started? Okay. We're on, it's 5.2. Did we get anywhere started on 5.2? I have a mark, but I think that was from last term. Did we get anything done in 5.2 last time? I don't recall. I think that's where we're starting, because I don't think we did Riemann sums. Oh, yes, we did. We did get started here. I marked the wrong place. Okay. This is the top. Well, let's go back. We did these, didn't we? Yeah. We did that. Okay. Couple of definitions here before we go any further. I think we ran out before we finished example 1, and that's why I had my mark where I did. On this example, this one that's shown here, it says calculate the Riemann sum. Remember, Riemann was Georg Friedrich Riemann. I think we talked about him last time. Oh, by the way, there is a paper due in this class. I require a paper. Most of the other instructors don't. You can pick any topic having to do anything with Cal 2. It could be a person, a theory, an application, how it relates to civil engineering, whatever you want to write on. But you need to pick a topic, and I mean, this is all on YouTube, but finding it might be a little tough now until I get the link there. No, y'all know how to find things on YouTube. Just look for this class on YouTube, the most recent. It's stated, what's the title of it? Probably syllabus, because I think we did all that first day of class. But anyway, you can hear all that, but you get to choose a paper topic. If you can write down on a piece of paper, hopefully this week, your name, what that topic, at least your first attempt at a topic is going to be. You can always change your topic if you want to. And then they also want your preferred email address. Because for years, the school was so stubborn, saying, no, we assign them an email, they need to check it. Well, most students, not most, a lot of students didn't check it. They used their preferred email address. Finally, this fall, they said, okay, we give up. We'll take the preferred email address. Still check the college email address, because something blanket gets sent there, and they may forget to send them to your other thing. And also your preferred phone number. Because a lot of times what's in the system isn't right. So that. Now, if your preferred phone number happens to be a cell number and there's a chance you may lose it or run over it with your car or get lost in your car or at home or somewhere and you won't have it with you, and the best way to get you is mama's landline and stuff like that, you can give that number as well. That's up to you. Or if you work, and I'm guessing as a baseball player you probably don't, so if you did work and might be at work and they're trying to get in touch with you and they can't use a cell phone at work, which a lot of jobs won't let you do, but you can take an incoming call there, you can get your work number as well. So, but anyway, I was just thinking Riemann would be a potential paper topic, and we talked about that last time. If you go and see that instruction, it'll be on Blackboard soon, but it'll also already be on YouTube, so you can go see it there. All right. Example 1, bottom of page 272. Oh, that's right. I wasn't going to do the example. One thing, we're just going slideshow here, but one thing I was going to do is, remember we said, what is the partition? Okay? The partition is the maximum length of your interval here. And in this one, you go from A to X1, so there's a partition, there's a second partition, and then they don't show them all. There's a partition, there's one, there's one, there's one. Here, that would be the largest subinterval, that would be the partition. this one, just looking at it, I would say either that one or that one. That looks like that might be a little large. Okay, so you pick the rectangle that has the largest interval, that your partition. That was part of that problem, but we weren't going to do the exercise. That's why we were on this one. All right. And y'all did do this last term, you think? Yeah. Last spring. Y'all did. Okay. All right. So let's just do these quickly. Here is rectangles defined by Riemann sum for alpha of x equal 8 plus 12 sine x minus 4x. I'm not going to check this and make sure they got it right, but let's take the word for it. At least we know that when x is equal to 0, they should be starting at 8. Sure enough, that looks good. And it's going up from there for a little bit, but then going down from there, and you can pick some other points. But this is what the graph looks like. How would you integrate that? Okay, you probably know how to integrate it, and we've sort of hinted at it already. But the Riemann sum, they picked points here inside the intervals. They chose the interval to be 0 to 1, 1 to 1.8, 1.8 to 2.9, and 2.9 to 4. Why they chose them, not sure, but just to give an illustration. What points did they choose? They chose 0.4. Can't tell you why they did that, but they did. 1.2, not too bad of a choice. I would have chosen something a little different. 2, that's not a very good choice. And 3.5. Just any values inside there. And we evaluate this at those 4 values there. Okay? Those are the 4 values we do, and then the Riemann sum would be the product of the area here, which would be this times that, the length times the width, plus length times width, plus length times width, and what's the bad news here? It's a negative length here, minus. So actually you're going to be subtracting that. Well, the area under the curve would be positive here, negative there, so you actually subtract off that part. Okay? And that's what they're asking you to do. Now, is this is leading to integration. This isn't integration. This is how you approach it. Okay? And that's what the problem is showing. Oh, this was the example. This was example 1. I'm sorry. I was thinking it was referring to the last slide. This is example 1. And again, because you've done it already, you have it. This is what Riemann sums are doing for you. Notice that last sum is actually a subtraction. Okay. Now, this leads to the definition of what a definite integral is. But before we get there, sorry, the Riemann sum, when you add those things together, okay, and remember, the limit was in the limit as that partition, that's the largest interval there, is approaching 0. That means all the intervals are approaching 0 if the largest one is. The partition of P is approaching 0 of your Riemann sum of that function that was given, what, 8 plus sine something or another minus 4x, okay? That function over this partition with that set of points, okay? The first one had 4 in it, but then as you let the partition go to 0, you get more and more and more of those. Just any interior values there. Okay. That then gets to be the summation from I to N as you let N approach infinity. They don't say that here, they say delta. The partition of P is approaching 0. This is the number of intervals approaching infinity. Alpha CI, that's what you get. CI came out of that set C. Delta XI, that is your maximum, that's what your partition is made up of, those delta X's. It's good. That's your height times your width, height times width, height times width. Do that many rectangles as you can as that approaches 0. That gives you the limit of that is your L. Now, that leads to this definition of the definite integral. Interval integral, okay. The definite integral of f of x over some interval, the integral of this over some interval, a to b, denoted by the integral sign, and think of that as that summation sign sort of stretched out. An integral is a summation over infinitesimally small increments, okay? So that's what the integral sign is from a to b. Those are the limits of the interval. F of x dx, that was your delta x, that partition that you have. This is what the limit is delta p, as the partition of p goes to 0 of that Riemann sum of that function f over that partition, okay, choosing whatever your set of interior points were, okay? And that would be the limit as that partition goes to 0 of your sum, I going from 1 to n, f of ci, delta p, delta xi, that's your partition, okay? And what you're doing then is letting this summation go to the integral. You're going from between the endpoints, the left hand to the right hand endpoint. Your f of x is from here. The delta, the dx is your delta xi. Okay? The thing, limit is that delta xi goes to 0, which is what that's saying right there. When that limit exists, then we say that f of x is integrable over that interval a to b. Definition of a definite interval. Definite interval has limits to it. Initial point, end point. Okay. Remember, and I think y'all probably did this last spring, your indefinite integral was basically your antiderivative. Remember that y'all did antiderivatives? We'll get to them. Don't sweat, we'll get there. Okay. Now, they have a little blurb here before the Theorem 1, and the little blurb is worthwhile. Let's go back to that description. Okay. I remember when I took calculus many decades ago, it got to be a little insulting to me, it seemed like, when they started calling the x a dummy variable. So, wait a minute, that's the independent variable. That's what everything depends on. But it's really a dummy variable. Once you do the integral, it doesn't matter what you put here. It's no longer in the picture anymore. So you could call this f of u du, as long as u is going from a to b. So the variable gets less and less significant here. And they do mention that the definite integral is often called more simply the integral of f over a to b, which they've already called it that. The process of computing integrals is called integration. F of x is called the integrand, what goes inside that, and the a to b are the limits of integration. I've already been using the terms, but I just wanted to point them out to you in the book. Then they have a conceptual insight here, and I think we've already hit that pretty definitely. We will come back and mention it with the fundamental theorem of calculus a little bit later. We haven't hit it yet, but especially that thing about the variable being somewhat of a dummy, okay? And you thought students were no, I didn't say that, did I? Okay. So, here's our first theorem. Now, let me make a guess. I bet you Mr. Racy really proved the theorems, didn't she? She's a mathematician. I was a physicist, okay? I'm not nearly as interested in proving theorems as I am applying it. I think most of the time, and here's my little view of the world from my perspective. Math is sort of a basic thing, okay? Physics is applied mathematics, and engineering is applied physics. I don't know if you see it that way, but that's how I look at the whole field. So I'm guessing y'all are a little more concerned with applying the stuff than proving theorems, but may not be. You may be lovers of theorems. I'm not going to spend as much time probably as you did on it. Here's theorem 1. If f of x is continuous, now what do we mean by continuous? No gaps, no holes, every value on the interval a to b, for every value in that infinite number of points in between a and b, every one of them f has a value, and there are no jumps. Okay, there is continuous everything on a to b. Or if f is continuous with at most finitely many jump discontinuities, then f of x is said to be integrable over a to b. If it has finitely many jump discontinuities, then you have to integrate over each of those intervals where it's continuous between the discontinuities. Okay? So then we say f is integrable over a to b. All right. Now, this is something we hit a little bit in the last, or one of those previous examples. The signed area of a region, okay? Again, I'm doing this pretty quickly. Signed area of a region is the area above the x-axis minus the area below the x-axis. Like we just saw that last example when you got down here, then you subtract off that part. Add the parts above, subtract the parts below. That gives you the signed area of a region. That defines what the integral is calculating for you. Okay? Now, here's the illustration of what they're saying here. If you were to integrate this function, whatever it is, this function here between a and b, this part would be added, this part would be subtracted. When I look at that, looks like to me the minuses win. You'll actually come up with a negative value, which is legal. It can happen. So the signed area is the area above the x-axis minus the area below. That's what the last slide before this one showed. Okay? Here's another, well, this is an illustration of that one done in Riemann. No, it's not quite that one, but similar to it in Riemann sum. Blow this up. These, by the way, did Mr. Rossi use the slide set? The PowerPoints? She did. I don't know if she mentioned them. I found them terrible. Okay? You have to blow them up in order to see them. Why didn't they make them big enough for you to see to begin with? So here would be from the Riemann sum going from A to B. This function wasn't the same one as before. But these all contribute positive values. They contribute negative values. The sum of those two basically will actually be awfully close to 0. Okay? But you do what it says. Okay? Now, here's example. No, wait a minute. Oh, I'm sorry. I thought we had already done this one. Okay? So basically, another way of looking at a definite integral is the integral from a to b of f of x dx is the signed area of the region between the graph of the function and the x-axis over a to b. It can be all positive, it can be all negative, it can be part positive, part negative, so the sum could be either a smaller positive or negative value depending on who wins. Okay. And this is example 2. We're not going to go over it per se. I bet you y'all did this last time. But this is y is equal to 3 minus x. And if you're evaluating that from 0 integrating that from 0 to 5, you see the 0 to 3 wins. 3 to 5 is going to be a negative value, so this is going to come up slightly positive. However, if you're integrating the absolute value of 3 minus x from 0 to 3, what you have to do is actually draw the graph. You can do this one once we do integration without ever drawing a graph. But if you're doing an absolute value, you almost have to draw a graph so you can see where your turn point is. This one you have to do one integral from 0 to 3 and a different integral from 3 to 5. Why? Because you're only doing this. So how you would do this is the integral from 0 to 3 of 3 minus x, that's this one, plus the integral from 3 to 5 of not 3 minus x, but x minus 3. This has to be positive. And how you make see, this is negative down here. If you're integrating the absolute value, you reverse the term. Here's a little bit of a reminder. If you're doing, here's how you define. Y is equal to, or f of x is equal to absolute value of 3 minus x. Okay? Anytime you have an absolute value, here's what that stands for. It's a piecewise defined function, and it's 3 minus x anytime x is less than 3. You can put the equal sign there if you want to. It doesn't matter. It's x minus 3 anytime 3. Let's do x greater than 3. Okay. Be a little bit nicer way of saying it. Basically, anytime absolute value function, it's this value anytime that value is positive. It's the opposite of that anytime that value is negative. And this is positive anytime 3 is greater than x, or equal to x. Allow you to zero in there. And it's the opposite of this anytime 3 minus x is less than 0. In other words, it's negative. If 3 minus x is negative, x minus 3 is positive. So that's what they're doing here. You integrate this part over there from 0 to 3, and then integrate this part, x minus 3, from anytime from 3 to 5. Because there, x is greater. So you do that, that's how you integrate anything with absolute value on it. You have to keep the value positive. Okay, and that may be reversing the terms if there's a minus sign in between. All right, let's look at some properties of the definite integral. Okay, here's a pretty straightforward one. I think we did one like this in 5.1 too, when we were talking earlier when we did antiderivatives. If we're doing the integral from a to b on the x, by the way, I hope you realize this, the dx here, whatever this is, those are the values here. X equal a to x equal b. Okay? These are values for x. Whatever your dummy variable is, those are the limits of that value. And your function here is a constant function c. So what is the area there? It's c times b minus a. The length of that's just a rectangle. Length times width. Okay? C is the width here, b minus a is the length. That's the integral of that. Now, I really want to get to doing integration the way you're supposed to, but this is all leading up to that, so let's live with it while we have to. Okay, so here is the theorem that verifies what we just noted. That anytime you're integrating a constant, for any constant c, the integral from a to b of c dx is c times the difference of b times a. There's no reason in the world to memorize that. Okay? Once we learn how to do integration, it'll make perfect sense, and we'll do it. They just haven't let us do that yet. Okay? So let's move on to theorem 3. Okay? Linearity of a definite integral. So let's say we have two functions, f and g. Both of these functions have to be integrable over a to b. Now remember what that was? They either are both continuous functions, or are finitely, have a finite number of discontinuities. Most of the time we're not going to worry with that. They're just integral functions over a to b. Then the sum of f of g is also an integral function, and some constant times f, or g, either one, is also an integral function. Now, I haven't quite figured out yet, I think I do know, but why they put capital C's here, most of the time we've been putting small c's there. And it really doesn't matter. I think I know, and you'll see it a little bit later. So if this is all true, since we said the sum is an integral function, what is the integral from a to b of f of g plus g, f of x plus g of x dx? Both of them being integral functions. Well, the integral of a sum is the sum of the integrals. Okay? Pretty straightforward, just what you would expect. That's the first half of any linearity principle. The second, if you have a constant times a function, that's just a pure constant, no x dependence on it, pull it outside the integral. The integral of a constant times a function is a constant times the integral of that function. Okay? And sure enough, that's the case. You combine these two together, and that enables you, especially in polynomial functions, but even functions that aren't polynomial, like one we saw earlier, you would be able to do it. I'm chomping at the bit to be able to do that. Okay? So let's move on. Here is an integral. Calculate the integral of that. Okay? And I don't know why they do it this way, but this is beginning to show you how to really do it. The antiderivative of the integral of definite integral from 0 to b. Well, that's sort of semi-definite, it seems like. 0 is a definite endpoint here, but b is an unknown endpoint there. So this is almost a semi-definite integral of x squared dx. Okay? Later we're going to get, in fact, right away we're going to get to the rule. But you did it in antiderivative, remember? You take an antiderivative, what do you do? Especially over a power function. You increase the power by 1, and then divide by 1 over that power. Remember how you do a derivative of a power? You take the exponent multiplied by the coefficient, drop the exponent by 1. When antiderivative or integration undoes that, so then the exponent goes up by 1 rather than down by 1. And whereas before you multiplied, now you divide by the last one. Okay? So that's your antiderivative. They haven't shown you that. They just say, oh, here it is. And then later they'll give you a rule. Why don't they give you the rule first rather than saying, this is what it is. Okay? And this was back in 5.1 when we were doing antiderivatives. We did this. All right. I feel like we really need to do that example, don't you? Okay, example 3. Let's do it. Okay. The integral from 0 to 3 of 2x squared minus 5 dx. Okay. Now, I don't know if you got familiar enough with it, you can do this one in your head. But if you can't, let's break it down into all of its pieces. That would be the integral from 0 to 3 of 2x squared dx minus the integral from 0 to 3 of 5 dx. And this would be the 2 times the integral of 0 to 3 times x squared dx minus the integral from 0 to 3 of 5 dx. Do I ever do this? No. Okay. After you get used to it, you just do them. Okay. But now we can use this rule right here that we did back in 5.1 and do it. This will be 2 times, what's the antiderivative of x squared? X cubed over 3, right? Move up the exponent by 1 and divide by that value, okay? Evaluate it from 0 to 3 minus, what's the antiderivative of 5 dx? Well, I should have done this. Let me go back and erase this. Let's write this as, pull out the constant 5, and you just have antiderivative of dx. So it'll be minus 5 times, what's the antiderivative of dx? X, exactly. When you take the derivative of x, you get dx, okay? So the antiderivative of dx would be x. That's evaluated from 0 to 3. And this will be what? So we plug in 2 times, what's 3 cubed? 27 over 3 would be 9. Okay. I'm sort of cheating a little bit here. Minus, plug in a 0 there. 0, okay. Not too creative there, is it? Okay. Minus 5, plug in a 3, and you get 3 minus 0, right? Well, this will be 2 times 9 minus 5 times 3. So this will be 18 minus 15. That's equal to 3. Okay? Does that make sense? Okay. Integration is not that bad. And would I ever split it up and do this way? Probably not. I would probably look at this way. What's the antiderivative of 2x squared? It would be 2 times x cubed over 3. So 2/3 x cubed minus antiderivative of minus 5 would be minus 5x. And then plug in that. And don't go through this. But if you don't see it well enough, break it down as far as you need to. Actually, like here I almost forgot to pull out the 5 because I never think of it that way. I would do this would be 5x. If you pull it out there and just do x here, then it's still 5x. Okay. All right. Now, here's another property of a definite integral. Okay? What happens if you reverse the limits of integration? All right? If A is less than B, we usually put the lesser on the bottom. Okay? But if you had A being less than B, but you wrote it this way, integral from B to A of f of x dx, if you reverse those numbers and put the smaller one on the bottom, larger on top, you have to negate the integral. It would be minus the integral from A to B. Integral from B to A of f of x dx minus the integral from A to B of f of x dx. And guess what? That happens even if those are reversed. If B is greater than, if A is greater than B, this is still true. Except that you wouldn't even want to do that if A was greater than B. Integrate it the way it is. But if you want it, if you needed to rewrite it, then you write that as minus. That's what happens if you reverse the order. You subtract, you negate the integral. Okay. The little side note here says, according to this equation, the integral changes sign when the limits are reversed. That's exactly what we're saying. All right. Now, here's another principle of integration. If you're integrating from A to A, you're not going very far, are you? In other words, you have a straight line. I mean, you don't have A to B under some curve. You have A to A under the curve. Well, guess what? Your dx is 0 then. So the integral from A to A of f of x dx is 0. Okay? I can remember when I took calculus, like I said, decades ago, my professor spent a long time proving that. Yeah, we believe you. I mean, it's the same point. I mean, how could it be anything other than 0? But he proved it. And it was a very straightforward classic proof. But my word. Straining a gnat to swallow a camel, but we weren't swallowing any camels anyway. Okay. Here is example 4. It says, prove that for all b, positive or negative, the integral, well, you can't see it. The book does this sometimes. It sort of drives me bonkers. They give the figure before they give the example that it's representing. Here's the figure, okay? No, they're not. This is something further on. Here's what they're trying to show, and let's just leave it like this. We've already done it. And their approach to it, I found, is rather backwards. But if you're doing an integral from 0 to b of x dx, okay, what's the antiderivative of x? Antiderivative of x. Okay. What's the exponent here? 1. Increase that by 1, you get 2. Divide by that 2. It'd be 1/2 x squared, right? Okay. And then evaluate that at b, 1/2 b squared. Evaluate it at 0. Okay. So that is indeed the integral from 0 to b of x dx, 1/2 b squared. All right. Now, how they went about showing this is what the previous slide was about, which is rather bizarre of how they do it. Rather than going 0 to b, x, they go from b to 0 and do the minus, and why? I do not know why they took such a long roundabout way to do it. So that's why I'm saying just leave it alone. That's what it is, okay. Now, here's the next theorem. Again, they got this time they put the theorem before the figure, but I think it's okay too. This is on page 276, if you're following it in the book. And again, we're just trying to make up for lost time. Additivity of adjacent intervals. Okay? We saw what happens if f and g are both integrable, then the integral of the sum is the sum of two intervals. But this time we're doing the additivity of adjacent intervals. Let's let a be less than or equal to b and b less than or equal to c. And assume that f of x is integrable over that whole interval from a to c. Then that integral from a to c of f of x would be the integral of a to b, because b is less than f of x dx plus the integral of b to c f of x dx. Why would you ever do this? What if you had a finite number of jump discontinuities? Then split them up. If it was discontinuous at b, then do a to b, integrate that, and then b to c, integrate that, add them together. That's when you use this. Does that make sense? Okay. But they have to be integrable over the whole thing. Yeah, so that's why you would use it. That's when you would use it. All right. And here is an illustration of this, okay? It's not particularly, I don't find a useful illustration, but it certainly is true, okay? If you're trying to get the area from A to C, and here's your f of x, no discontinuities there, nice, smooth, continuous function, just integrate it, okay? But what they're saying is, if you knew A to B, and then wanted to just calculate this, or calculate this and use that, or just wanted to calculate them separately, because they're different to do, then do that. Integral of A to B of that function f of x will give you that area plus B to C will give you this area. That's the same as the integral from B to C. That's it. Okay. Yeah. Looks like exactly what you would hope, and it is what it is. All right. Now, here's another thing. This is leading to example 5. Sometimes they give the figure before the theorem, and sometimes they give it after. Here they've given the figure before. What if you're interested in the area between two functions? Okay? I think that's, no, that's not what they're doing, but it would work. Okay? They're comparing. If f of x is always larger than or equal to g of x, but never less than g of x, then the integral of f of x is always going to be greater than the integral of g of x. That kind of makes sense, doesn't it? The area under that curve, if this curve is always greater than that one, then the area under this curve is going to be greater than the area under this curve. All right, pretty obvious. Now, where this is going to lead later, if you're doing the area between two curves, it would be the area of this curve minus the area of this curve. That would give you the area between the two curves. So that would be another one. That's not what they're doing here. Coming close to it, but not quite. Okay? And that's the comparison theory, which seems to be almost self-evident, but just to be complete, they'll put it here. Comparison. If f and g are both integrable functions, and g of x is always, always, always either less than or equal to f of x, but never greater than, always less than or equal to f of x, for all x's in that interval a to b, then the integral of g of x has to be less than or equal to the integral of f of x. Because f of x is greater, and you're integrating that, you're going to be having larger heights, okay? So it's got to be that way. Is this making sense? The question is why? I mean, why do they spend so much time on this? All right, now this is an interesting little kind of problem here. The red curve here is y is equal to 1 over x. The blue curve here is y is equal to 1 over x squared. Okay? Now, these are equal at x equal 1. Now, obviously, this graph is not quite as symmetric. The y scale is expanded, x scale is somewhat compressed. But that's those two graphs. At x equal 1, both of these values are at 1. So when you're less than 1, 1 over x squared is greater than 1 over x. When you're greater than 1, 1 over x is greater than 1 over x squared. So if you're doing the integral between the curves, you have to have stop and do one, do it one way less than one and another way greater than one. Okay, that's not what they're doing here, but in the future you'll see that we'll use circumstances like that. Okay. Now that leads then to another that leads to example 6. When you're going integrating from 1 to 4 there, you always put the 1 over x on top of, if you're integrating that on top of 1 over x squared, but if you're just comparing them, then the integral of 1 over x squared would be less than the integral of 1 over x. Now, we do a little bit about upper and lower bounds. Again, we're just doing highlights here. We'll get to do the real stuff in just a little bit. Not soon enough, but just a little bit. Here is an integral. Integral from a to b of f of x. There's your f of x, the pink line, the red line. F of x dx. That integral, that function, lies between the constant function capital M, which is the maximum value f of x takes on between a and b, and the minimum value that it takes on between a and b. Okay? So this function itself has to lie in between m times b minus a, capital M times b minus a, and little m times b minus a. The area under the curve is in between that one and this one. Okay? It's greater than this one by that amount, less than this one by that amount, so it's always in between. So, if you thought you were through with dealing with finding max and min when we did derivatives, you're not. You're going to be finding them again here too. Okay, and this illustrates what that last was showing, that the area, little m times b minus a, is less than the integral from a to b of f of x dx, when little m is the minimum value of this between 0 and b, capital M is the maximum value of f of x between 0 and b, then this integral is going to be between the little m times b minus a and capital M times b minus a. It's true. I can't think of many times you're really going to need that, okay, but it's true. And the final one is then this is the figure that goes with example 7, which we're not going to do, but it illustrates that point. The integral between 1/2 and 2 of 1 over x dx, and this is y is equal to 1 over x, and y is equal to x to the minus 1, same value. Okay, between 1 and 2, well, this value is going to be 2, this value is going to be 1/2. Well, that's this delta x here, you might say, is 1 1/2, right? So that would be 3/2 here. 3/2 times 1/2 would be 3/4. So the area under this curve is greater than 3/4, but less than 2 times 3/2 would be 3. So it's going to be 3/4 and 3. It's a pretty big range, but that's all they're asking you to do. Okay. That was it for 5.2. And is this worthwhile? I mean, not doing any examples really, so to speak, but are you following us okay, that what it's trying to show you? I think once we get to doing the real stuff, hopefully just the fact that you say, what am I doing? Okay. So let's move on to 5.3. The indefinite integral. And part of this we did, and by the way, the slide set that I've got is not with this text, it's from the previous edition, okay? Some of this was done at the end of chapter 4. Antiderivatives was a section at the end of chapter 4 in the old one, and it's part of 5.3 in this one. But I think they repeat the stuff, so if they don't, I'll repeat it for you. So let's get the slideshow set up from the current slide. All right. I think we already covered antiderivatives and the general antiderivative. And what the indefinite integral. We did all that last time. The power rule for integrals, we did that. We've already used it today. The antiderivative for 1 over x. I think we did that one before, didn't we? Antiderivative of 1 over x. You remember what it is? What? Not x. The antiderivative of dx would be x. Antiderivative for 1 over x dx. What function, when you take a derivative of it, gives you 1 over x? No, that's an equation. Log x. ln x. The derivative of log x is 1 over x. So the antiderivative of 1 over x is log x. Okay? I think this whole section here is what we did in 4.8 or something another a little bit earlier. You can watch it on YouTube if you don't remember this from before. I think what we're in now is what in this, yeah, we're in 5.4, okay? Because what was 4.8 in the old edition is 5.3 in this edition. We've already done all that. So let's jump over to 5.4. Fundamental Theorem of Calculus, Part 1. There's 2 parts of this. This is Part 1. And basically, it's what I've been doing, because I just was sick of waiting for them to get to it. It's how you do definite integrals. Fundamental Theorem of Calculus, Part 1. Assume f of x is continuous. Remember, that's all it takes to guarantee that it's integrable. It has to be continuous on a to b. In fact, it could have a finite number of discontinuities and still be integrable. So we're going to have it continuous on a to b. If capital F is the antiderivative of little f, which is what I jumped on in and had you doing, on a to b, then the definite integral from a to b of f of x dx. If capital F is the antiderivative of little f, then that's capital F evaluated from a to b, which is capital F of b minus capital F of a. That's what we've been doing, right? Fundamental Theorem of Calculus, Part 1. Okay? Now, I'm sure Mr. Racy would have proved this, okay? That should have been in the last course, so I'm not going to take time to prove it now, but basically, here's what you get. F of b minus f of a would be the summation of all your, if you do f of, yeah, I almost have to have a figure with this too. They didn't show the figure, but if you divide that into a partition, in elements of the partition, and you do f of xi, which is going to be ultimately the right-hand side, minus f of xi minus 1, which is the left-hand side, and you start with this, so fairly simplistic. The very first one of these, when it's equal to 1, that's going to be f of a. So f of 1 minus 1, 1 minus 1 is f of 0, that's f of a. And then f of x1, the next time you do one, it would be alpha of x2 minus alpha of x1, when alpha of x1 cancel out, and all of them cancel out until you finally get to alpha b. So it gives you this fundamental theorem of calculus, okay? There's the figure that sort of illustrates it. If you did, some. All right. Now, this is your function y is equal to alpha of x. That's your capital alpha of x. This is a result of the integrating antiderivative of little alpha that we're not even showing here. So here's alpha of a, which is a is x0. Okay. And the first one then would be alpha of x1 minus alpha of a. Okay. So the second would be alpha of x2 minus alpha of x1. You had an alpha of x1 here minus alpha of x1. Those add to 0. These add to 0. Those add to 0. What are you left with? Alpha b minus alpha of a. So that's a really, I guess, sort of simplistic way of looking at fundamental theorem of calculus, part 1. That's what you get. You're doing your increment. No matter how small or how big or whatever your increment is, you're doing all these pieces here, and if you do one minus the upper one minus the second one, the last one is going to be a minus alpha of a, and then all the pluses will be the next one's minus. This one's plus will be the next one's minus. You know, so they all cancel out until you get here, and you're left with alpha b. So alpha b minus alpha of a. Again, the figure really doesn't help a lot, but the summation part is pretty straightforward. All right. And to me, they just beat this into the ground. I'm trying not to do that as much here, but they sort of talk about a tale of two graphs at the top of page 290, and again, it's just reiterating the fundamental theorem of calculus part 1. And trying to see the relationship between these two graphs. I'm not sure I'm seeing these at all. Yeah, okay. If this is this, the antiderivative of this thing is going to be some positive value. And then you're adding to that the antiderivatives of the other. As long as alpha of x is always positive, then this sum is getting greater and greater and greater. But every one of these is canceling the previous one, so you wind up again with alpha b minus alpha of a. Okay. Same thing we did before, but now they're doing it with this. But now they're showing where do you get this. This is the sum of this one. That's the sum of this one. That's the sum of this one. And that's somewhere there. And again, it's almost patently obvious, so why are they beating it to death? I don't know. All right. Now this one I think is probably worth doing. This should be example 1. No, it isn't. This is example 2. Okay. This is a graph. Thank you for graphing it for me. I'm glad I didn't have to graph this one. G of x is equal to x to the minus 3/4 plus 3 times x to the 5/3. Okay. It says integrate that over 1 to 3. 1 to 3. Thanks for drawing it. Glad I didn't have to do that. So let's do that integral. Well, I have to shrink this down again and get my thing back. We're doing the integral from 1 to 3 of x to the minus 3/4 plus 3x to the 5/3 dx. Okay? Now, antiderivative of x to the minus 3/4. Remember how to do that? Okay, x to the 1/4. Okay, how did you get that? You added 1. 1 is 4/4 to minus 3/4, and you get x to the 1/4. Okay, that's good. With what? Second? No, over 1/4. Okay, over the exponent, right? But what is 1 over 1/4? 4. Okay, so that would be 4x to the 1/4 plus, what would this next one be? Eight thirds. X to the 8/3. Okay, you got a 3 there. Can't throw that away. X to the 8/3. What we're going to have to do. It would be over 8/3, which is times 3/8. No, 8/3. 3/8, right? Second? Yeah. It's this exponent over 8/3, which is the same as times 3/8, right? Dividing by 8/3 is the same as multiplying by 3/8. So then you'd be multiplying by 3 over 8. Okay. All right, so far? We're evaluating this from 1 to 3. Okay? Now, that would be 4x to the 1/4 plus 9/8 x to the 8/3. Okay with that? Evaluated from 1 to 3. I'll do the 1 part, you do the 3 part. Okay, no. What would this be? 4 times 3 to the 1/4. Let's just leave it alone. I don't know what the 4th root of 3 is. Let's leave it as that. Plus 9/8 times 3 to the 8/3. Okay? I don't know what the cube root of 3 is either, so I'm not going there either. Okay? Minus, but the minus sides we can do. What would that be? 4. Oops. Because it's a minus here too. Oops, that's not what I wanted. It's also a minus. Okay. Started to put plus. 1, if you put a 1 in here, that would just be 9/8, right? You put a 1 in here. Put a 4 in there for this part. You put a 1 in there for this part. The 4th root of 1 is 1. And the 8/3 root, the 3rd root of 1 is 1. And 1 to the 8th power is 1. So that would just be a minus 9/8. So, weird number, but that would be what you get. Now, 4 times 3 to the 1/4 power plus 9/8 times 3 to the, can I read that, 8/3 power minus, that'd be 1 1/8, so that'd be 32/8 minus 9/8 would be minus 41/8. whatever you got minus 41/8. And then you would have to do this on your calculator. And you can do it with exponential notation, 4 times 3 to the caret 1/4. I'm sure you put the 1 over 4 in parentheses, plus 9/8 times 3 to the caret 8 divided by 3, close parentheses, minus 41/8. Or if you want to do it another way, some of the older calculators, you have a fractional form here and you do it that way, or you can do the 4th root of 3, and this would be the cube root of 3 raised to the 8th power. However you want to do those calculations, do them, but they tell us it comes to something about 21.2, which I'll take the word for. But I wanted you, what the answer is as important as how you got there. And y'all did the integrations well. Was that okay? Did you get the same thing they did on your calculator? I see you were doing it. Not yet. Okay. What kind of calculator you got? Huh? Not a good one. You don't have a caret key, so that's the problem. So here's what you would use. You would use this key. Okay. Yeah. And I mean the shift of that key. So for you to use this one, here's how I would write that problem. This would be 4 times the 4th root of 3. That's exactly what you got there, right? You got a calculator, a key that does that, right? Okay. Plus 9/8 times the cube root of 3, and then raise that to the 8th power. Then minus 41 over 8. Okay. So this one will be that shift, blah, blah, blah. Do your phones do this? You have to turn it sideways, I think. I don't know if you got an Android or not. I've seen how to do it on those. I've done it once, but see how that works. This part. Huh? I'm sorry. Can't hear you. Yeah, this parentheses.
Yeah, what's the number?
That's 8. The exponent is your power. The numerator is the power, and the denominator is the index of the root. Get it? Good deal. Did you figure out, I don't know if calculators can do those kind of things or not. Have you found it yet? Okay. It's not a huge issue. If you need a calculator, we can get you a calculator. But. Okay. Just because, okay. Did you need that any longer? This one. Okay. And by the way, I don't know if you gathered it or not. I'm hard of hearing. So if I ask you something, it's not because I can't hear it. Okay. All right. Here's one that we all knew and love. Calculate the integral from minus pi fourths to pi fourths of secant squared is this redundant for you, or is this worthwhile?
We did. I don't think we did this.
You don't think we did? You did? Okay. So from here we'll pick up and go then. Is that right? Okay. Integral from minus pi force to pi force of secant squared x dx. Okay. Now, when you're doing integration, you got to think of differentiation in reverse, right? Antiderivative. Okay. Can you think of any function that when you take the derivative of it, you get secant squared? See, he's got a cheat sheet. Oh, you don't have a book yet, do you? Huh? It's at home. Oh, that's good and safe there. That can't get lost there, can it? All right. If you go to the back inside cover, go back a ways inside, differentiation shows up on some of the pages toward the end there in the text. It's a hardcover page. Differentiation rules, there are differentiation rules. Trigonometric functions. This looks like a trig function, doesn't it? Let's go by and look at those. Oh, look at number 15 back there. It says d by dx of tangent x is equal to secant squared x. We knew that, didn't we? So the antiderivative of secant squared would be tangent x. So this will be tangent x evaluated from minus pi force to pi force. Okay? So this means, what is tangent of pi force minus tangent of minus pi force? Okay? What is tangent pi force? Anyone remember that? Oh, sure we do. One. Oh, very good. Minus, and what's tangent of minus pi force? Let's just draw the tangent function for you real quickly. If this is 1 here at pi force, it's negative 1 minus a minus 1, and what does that yield? 2. Got it. So that's that. Okay. Okay, that one done. Let's do example 4. What we're going to do here is the integral from 0 to pi of sine x dx. Does anyone remember what the antiderivative for sine was? In other words, when you take the derivative of some function, what gives you a sine? Negative cosine, excellent. So it'll be a negative cosine x evaluated from 0 to pi, which would then be minus cosine pi, right? Minus a minus, which is plus cosine 0. That's not a theta. It should be a 0. By the way, if you haven't noticed already, I slashed my zeros. I was in the Navy, and we always learned to slash zeros so you wouldn't confuse it with an O. So, and Z's, I slashed the Z so you don't confuse it with a 2. And it's just an old habit I haven't gotten away from. That looks like a phi, but it's not a phi, it's a 0. What is cosine of pi? And minus that would be 1. What's cosine of 0? 1. So that would be 2. Oh, we're stuck on 2s, aren't we? Okay. Now, the b part of this, though, would then be, what's the integral from 0 to 2 pi of sine x dx. Antiderivative of sine is still negative cosine, evaluated from 0 to 2 pi, which now in this case would be what? negative cosine of 2 pi plus cosine of 0. And what's negative did it again. Whenever I'm writing cosine, I want to write an angle after it, and so I put a theta, and I need to put a 0. Okay. And what's cosine of 2 pi? And minus, that would be a minus 1 plus 1. What's that equal to? 0. Does that make sense? Because now you're doing the area under the curve here. This is a positive area here. This is exactly the same negative area here. Sure enough, that adds to 0. All that to get nothing. Okay. Got it. All right, that was so much fun. Let's do another one. Here we have the integral of from negative 0.3 to positive 0.6 of e to the 3x minus 1 dx. Uh-oh. How are we going to do that one? There is a way in a few classes that we're going to do that that's going to be really, really easy. But we aren't a few classes into the future yet. So we can't quite do it the really, really easy way. So what we have to do now is do it a little bit different way. Okay? Now, I want you to remind me of what a to the b minus c is. Maybe not. Would that be the same as a to the b? Let's see. Let's back off one. Okay. And do let's put a value in there. 2 to the 3 minus 1. We can do that, can't we? What is that? 2 squared, which is 4. Now, would that be the same as 2 cubed over 2 to the 1? Remember that? And what was 2 cubed be? 8 over, second, 2, and that's equal to 4. Okay, now let's do this one. What you reckon that would be? A to the b over a to the c. Would you buy that? Okay, I got some swampland down in Florida also. No, okay. If you're that gullible. Okay. So let's do it with what we got here. This would be e to the 3x minus 1 would be the same as e to the 3x over e to the 1. Right? Okay. You all right with that? Now, so would that be the same as the integral from minus 0.3 to 0.6 of, well, guess what? 1 over e to the 1, that's just a constant, right? So let's bring that 1 over e. This is 1 over e. You don't have to put the 1, right? Times the integral of e to the 3x dx. Okay. Now, I love exponential functions, the e function. Why do I love it so? What's the root of e to the x? And what's the integral of e to the x? E to the x. I love e to the x because it's so easy to integrate and so easy to differentiate. It's always the same. We do have a constant here. Now, if we take a derivative of that, what's the derivative of e to the x? E to the 3x. We're not doing it. This is just a rhetorical question. Derivative of e to the x, e to the 3x. Say again?
Would it be log 3x?
No. Derivative of e to the 3x would be e to the 3x, right? But you have to do a chain rule and do it times 3 then, right? Okay. This is d of e to the 3x dx. Okay. Derivative of any exponential function, e to the something or another, is itself e to the 3x. But then because of the chain rule, you would do times d by 3x dx. And what's that? Derivative of 3x. Huh? 3. That would just be 3. So, that would be your derivative of e to the 3x. But we're doing an antiderivative. Okay? Antiderivative will still be, and we got 1 over e out front, and we got e to the 3x, but when you take a derivative, you multiply by 3, so as soon as you're doing an antiderivative, what are we going to do? Divide by 3, you got it. So that's going to be dividing by 3, and this is going to be evaluated from minus 0.3 to 0.6. Okay? So what do we have now? I'm all over the board here, sorry about this. This is 1 over 3e, e to the, okay, 3 times 0.6 would be 1.8 minus e to the negative 0.9. Do you buy that? Plug the 0.6 in for the x here. That gives you 1.8. Now what I did, I took the 1 over e and 1 over 3 together, so it's 1 over 3e. That's your constant up front. Then you're evaluating just this part. That. E to the 3 times 0.6 is 1.8, right? Minus e to the 3 times negative 0.3, which would be negative 0.9. Okay. Another real fun number. One of my favorite numbers of all time. No, really not. Okay. So you need your calculator to actually do this. Do they even come up with an answer? Yeah. They actually did it a different way, and I'm not sure shame on them. Okay. Well, they did it basically the same way. I bet you we come up with the same answer. They get something like 0.692. Let's see if we do. Have you already done it? You got the same answer. They just integrated that thing, and they told you it's 1 over 3 times the integral of that. And I guess it's okay to do that. It's e to this thing times the 1 over the derivative of this thing, which it comes out the same answer, but I didn't think we had. We'll see later. There's a much easier way to do it, but since we didn't have that, I didn't do it. Now, there is, I think, another example here, but they do this first. Okay. And this is one I asked you about earlier, and we hemmed and hawed a little bit about it, but then I gave it to you. The integral from a to b of 1 over x dx, or dx over x, or x to the minus 1 dx. However you like that. What is the antiderivative of that? Log x, natural log of x. So it's natural log, and guess what? We cannot ever take the log of two things. What? 0 or negative numbers. So therefore, if you're going to evaluate this, you have to put absolute value of b minus the absolute value, the log of absolute value of a, because you cannot take the log of Now, what does that give you? Well, that's the log of, this is the property of logarithms. The log of something minus the log of another thing is the log of the top over the bottom, log of b over a. And notice they left off the absolute values bar there, because if a and b were both positive or both negative, it wouldn't matter, because then it still comes out b over a. Now, what you would have a problem was if one of them was positive and one was negative, then you do have an issue there. But we're going to assume that they're such that you can do that. Okay? So that's one thing to kind of keep in mind. Now, they do say when A is negative and B is positive, this doesn't work. It's only if both A and B are positive or both A and B are negative. But you know, you want them to both be the same anyway. If you think about what your 1 over x function looks like, okay, whoops, can't do that. Here's what 1 over x looks like. That's when x is positive, that's when x is negative, right? This is really ugly graphing, but you got the picture, right? Do you want to ever take something integrated from here to there? You've gone through a couple of infinities here. That's not a function that's integrable. You see why? This is not a jump discontinuity there. That's an infinite discontinuity. You cannot take it. That's not a continuous function, and it's not a removable jump, or a jump discontinuity either. So you can never take it when A is negative and B is positive, or vice versa. You can do it if you're over here, or you can do it if you're over here, but you can't do it across that. So if you're over here, then make that, and both of these being negative, that divided by that, you can throw away the absolute value bars. If they're over here, you don't even need the absolute value bars, log b minus log a, which is log of b over a. Okay? So that works only if they're both positive or both negative. All right. All right, let's do this one. Goodness gracious. Oh, that's the, I was trying to, let me blow it up for you, make it easier to see. I can't get all three of them on, so let's just do the first two. And then we'll do the second two. This is the generic one. Integral of 1 over x, a to b, is going to be this. You don't need the absolute values there if both a and b are positive. It's just b over a. That's it. You do not need the absolute value bars. So why they put them, I'm not sure. So the next thing is the A part of example 6. Okay, so let me do it. This is the A part here. The integral, no it isn't. Yeah it is, oh here it is. From 2 to 8 of dx over x. What would that be? Antiderivative of 1 over x dx? ln x, evaluated from 2 to 8, which would be ln 8. That's ln 2. Now, that would be ln of, no, 8 over 2. Okay. Now, here's why that is. This is ln 8 plus the log of 2 to the minus 1. Okay? And then you're multiplying the log of a product is the sum of their logs. Okay? The log of a difference is the quotient of the logs. So that gives you this. I mean, whichever way you want to do it, that would be log of 8 times plus log of 1/2, that's 1 over 2, and that would be the log of 8/2. However you do it, which is the log of 4. Okay, what is the log of 4? You can plug that in your calculator and see. ln log. .39. And that's what this gives you. Okay? Now, the other one that they're giving, that's the C part here, is the integral from -4 to -2 of dx over x. Yeah. And that would be ln of x evaluated from -4 to -2, which would be say that one more time. I was afraid you said that. You can't take the log of a negative number. So you do the log of absolute value -2 minus the log of absolute value -8, which would be the natural log of 2 minus natural log of 8, which would be the log of 2 over 8, which you could have gotten from just doing the -2 over -8 would be 2/8, which is 1/4, which would be second. Oh, I'm sorry. Why did you do that? That was a silly thing to do. You're leading me astray, aren't you? Okay. Okay. Let's see if you can get it right this time, okay? What's log of 1/2? Negative. Okay, something 0.69 or something like that. And that's what we got in the book too. Does that make sense? Yeah. This curve is below the x-axis, so the area under the curve would be a negative value. It does make sense. It has nothing to do with being left of the 0. It's that it's below the x-axis. All right, good deal. Now, it's be up to you how much you want to do on this. But if you feel like you need some practice on these, do either 1 or 3 or both, and then do any of the odds 5 through 41. I'll let you choose how many you need to do. If there's any of those that you can't figure out how they got those answers, bring them back to class. Any of the odds 43 to 47, and any of the odds 49 to 53. You can do 55 if you'd like, and you can do 57. I think that's pretty easy. In fact, I'd say do any of the odds 55 through 61. The 61 may be only a wording. You can always do any of the further insights and challenges, the odds that you're interested in. I'm not going to assign them, and I won't ask questions like them on the test. So any questions on 5.4? So you didn't do, I don't know why I hit that key. You didn't do fundamental theorem of algebra part 1 or 2? Okay. All right, well then let's go on to how are we doing on time? We got, what time do we put? Yeah. It's what? We go to 11:10. We just passed 11:10, didn't we? So that was a very good place to stop, wasn't it? So his bladder was correct. Okay. We'll start 5.5 next time. Okay. So I guess we'll do the, and this is a very, very short section. So we'll do that. And I'm real tempted to skip 5.6. It's a good section, but we really need to move on. And we'll start, after we do 5.5, which won't take us long, we'll move right into 5.7, which is substitution method, which is where I was going to begin. This is where your testing will begin. So we'll do that. Okay? All right, good deal. So why did I even open that? I don't know. You had me do it, didn't you? All right. All right, good deal. All right, take care.